Hey guys, Miss Peterson here, and welcome to our chemistry lecture on electron configurations. In this lecture, we're going to be going through how to use the periodic table to write electron configurations for our elements, both regular full electron configurations and shortened or noble gas electron configurations. So let's get started. So first off, we need to understand how electrons are described in the quantum model of the atom. Now, this goes a couple layers deeper than the Bohr model of the atom. There are 4 quantum numbers that describe kind of the address of electrons and describe where they are in the atom. The first of this is one you're familiar with. It's the energy level, okay? Remember, that's given to us by the rows on the periodic tables, and they go up in energy as that atom expands. These are what is accurately, what is represented in Bohr models. Now, our ones that we're going to go deeper in with our electron configurations are the orbital. Now, the orbital refers to the actual shape of the probability distribution of the electrons. We have s orbitals that are more spherical, p orbitals that are infinity shaped, d orbitals and f orbitals that get into all kinds of crazy shapes. Okay, these are what those shapes kind of look like. So each of these orbitals can fit 2 electrons. So there's only one s orbital. S orbitals can only fit 2 electrons. But there's 3 p orbitals, one orientated along the x-axis, so one along the y, and one along the z, meaning that p orbitals can fit 2, 4, 6 total electrons. Okay, d orbitals 10, f orbitals 14. Okay, so we should write that in. 2 electrons max, 6 electrons max, 10 electrons max, and 14 electrons max in our d orbitals. Yep. So what about the 2 others? These are subshell and spin. Now, these aren't really that represented in Bohr models. You have to go into something called orbital diagrams to actually get into these, but they have to do with either which specific orbital it is in for subshell, is in the px, the py, or the pz, okay? And then spin can be up or down depending on the electron. Okay. Now, when we write electron configurations, what we are representing is the energy level and the spin of each individual electron in the atom. So let's see how we do that. Okay. We use the periodic table, and we're going to segment our periodic table, okay? This image that you see on your screen is what I want you to kind of picture in your head, overlaid over this periodic table. So we have our S block here, okay? And then this is our D block, okay? The big transition metal section. And then our P block, these groups right here. Now, there is one exception to that, and that is helium. Though helium is over in the P block, it is actually the 1s2 element, okay? So when we write our electron configurations, we are going to read the periodic table from left to right until we get to our element, okay? So again, picture this image in your head, and I'll overlay it over it as we go, but let's look at some examples. Oh, before we get to that though, I want to point out one thing. In our S block, you'll notice that the groups just follow the period or row number. And that is also true for the P block. Okay. However, for the D block, you'll notice it goes down by 1. It goes 4s and then 3d. Because the d orbitals are higher in energy due to their funky shapes, okay, we actually fill in 4s electrons in the 4th energy level before we go back and fill in the 3d. So D we'll always say is kind of n minus 1. Okay. And then if you remember, our F block elements are actually inserted kind of up in there. So for these ones, you'll note that even though it's 6s, it goes to 4f. So for the F block, it's going to be n minus 2. Okay. Okay. So let's see how we actually use this. So we're going to start from the 1s orbital and fill in electrons from the lowest energy levels to the highest energy levels. And because we're filling them in from the lowest to highest, one of the ways you can kind of think of it is reading left to right across the periodic table, because hydrogen only has one electron. So that one electron would be in the lowest energy level. Second lowest, third lowest spot, fourth lowest spot, and the electrons will fill in as they go. So we can do that as well. Let's look for oxygen, okay? Oxygen is right here on the periodic table. It is in the P block, so we know it's going to end in 2P, but we start at the top. So our S block, our first row, we have 1s. And then you count 1s, 1, 2. Or you just know that 2 electrons max can fit in s orbitals. So the first 2 of oxygen's electrons are going to go there. Now, oxygen is number 8 on the periodic table, so we are going to be placing 8 total electrons. And in our configurations, just as a reminder, okay, the top number represents the number of electrons. And that 1 is, of course, the energy level, and the S is the orbital. Okay, so we got 1s2, that's 2 of our 6 electrons. Or of our 8 electrons, we got 6 more. Let's keep on going. So after 1s2, we're in the second energy level, S block, 2s2. And then we're over here in the P block, still in that second row. So 2p, 1, 2, 3, 4. 2p, 4. We stop when we get to oxygen. Now you can see we have, we have 2 plus 2 plus 4, which adds up to the 8 total electrons. You can also see in the second energy level, it has 2 plus 4 or 6 electrons. So that matches that oxygen has 6 valence electrons. Okay, cool. Okay, cool. Now, when you look up how to do electron configuration, sometimes you'll also see this method where you fill in a row, okay, like here. The first energy level has a 1s. The second energy level has s and p orbitals. The third energy level has access to s, p, and d. And you fill it in this kind of zigzaggy pattern going down that way, okay, going 1 through there, through there, through there, okay. So that is another image you can use if you prefer that to the periodic table. Okay, let's look at a slightly harder one. Nickel. Okay, nickel, Ni, is right here on the periodic table in the middle of the D block of elements. Okay, so let's go ahead. It has 28 electrons that we're going to be placing. Okay, put back on red. We start at the top, and here we go. We have 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s2, 3p6, 4s2, and then we get to the D block. What do we have to do with the D block? We go down an energy level. So even though it's in the 4th row, this is going to be the 3D. And we have 1, 2, 3, 4, 5, 6, 7, 8 until we get to nickel. So 3D, 8. Okay, cool? Okay, cool. Let's try one more. Let's do a really hard one. Now, in the context of this class, I'm only going to expect you to be able to write electron configurations up to that 4th row with the 3D orbitals. But you should know how to do them in case you're interested on ones that even include the F block. Okay, so let's try one of those. We're gonna do uranium. Okay, down here, number 92, all the way in that's the 7th row. So that would be the 5F4 or 5F3 position, okay, depending on who you talk to. But let's go ahead and see how we would write this. Okay. It's going to be long, so write small. We're going to start at the top and work our way through. I'm going to go kind of quickly in the first couple, and then I'll start slowing down when we get into those f orbitals. So we start at that top, and we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, and then after the 3d, we're up back in the 4p. So 4p6. Okay, after the fourth, we're down in the fifth. 5s2, 4d10, 5p6, 6s2. Okay, now I'm in 6s. Oh, and then what happens? Okay, after 6s, then I'm in the f block, and those are -2. So instead of being 6f, it's going to be 4f. So 4f, and they're going to be 14. Lawrencium and actinium are actually up here in the D block, but sometimes that's argued a bit, so just know that 14 fit in the D orbitals. Okay, 4f, 14. Okay, then we're in the D, which is -1, so that'll be 5d10, 6p6. Okay, and then we're down here, 7s2, 5d, and to get to uranium, we have 1, 2, 3. Again, lawrenium and actinium are up here in the D block. Okay, it's just kind of written weird on this periodic table. Hopefully it is more clear on yours. But it would be 1, 2, 3 to get to that uranium. So 3d3. And then let's check and make sure that all of our electrons add up to our 92. Ooh, nope. It is 3d4. I lied. 3d4. Okay, cool. Because we need all of our electrons to add up to the 92 electrons. So 2, 4 plus 6 is 10, 12, 18, 20, 30, 36, 38, 48. 48 plus 6 is 48, 49, 50, 51, 52, 53, 54, 55, 56. 56 plus 14 is 70, 80. 80 plus 6 plus 6 plus 12, 92. We got all of our electrons, okay? And that was miserable, okay? Do you ever want to do that again? No, probably not. You want me to teach you the shortcut? Okay, let's go for the shortcut. So sometimes we use abbreviated electron configurations. These are called noble gas electron configurations. So for that long uranium one that we just wrote, instead what we would write is radon. Okay, hey, it has all of the electrons just like radon has. And then in addition, you just continue your electron configuration from there. So I'm at radon, and then it's 7s2, 6d4, okay? Or 5f4. So let's try it for sulfur, okay? Well, who is the noble gas? Reminder, that's our group 18 elements, okay? Sulfur is right there. The noble gas above it is neon. So we say, hey, sulfur has electrons just like neons. But then it also has the 3s2 and the 3p4 electrons. Okay, cool. Let's try another one. What about silver, Ag, right here on the periodic table? Okay, it's in the D block, so slightly more challenging, but we go to the noble gas in the row above, which is krypton. And we say, hey, silver's got all electrons like krypton has, but then it also has, let's see, there's krypton, 5s2. Wait, that shouldn't be 5, that should be 6, right? Oh no, that's right. 5s2, 4d1, 1, 2, 3, 4, 5, 6, 7, 8, 9. 4D9. Okay. And that's how we write our noble gas electron configurations. Okay. That's it. Okay, cool. Okay, cool.